In the last lecture we discussed about the line integral, and I said in the last that there is some condition. If that condition satisfied, then line integral is path independent. Okay, so I will give you the condition now. What is that condition under which the line integral only depends on the end points of the path but not on the actual path taken by that particle or that whatever the vector field. Now let's start from the fact that we have discussed in the lecture of the gradient. We discussed in the lecture of gradient that, let's say initially I am some point A, and if I am moving from point A to infinitesimal small distance in this direction, and let's say the magnitude and the direction is given by some di1 vector. Okay, so from point A I am moving di1 magnitude, and the direction is also given by this vector. So if I want to find the change in this fxy surface, which is in the g direction, okay, so let's say from point A, the height of this surface is at this point, and at this point the height would be like this. Okay, now if I want to find the change from point A to, let's say this is some point A1. Okay, this is point A1. So from point A to point A1, if I want to find this change df, then we discussed and we derived one expression that this df is given by gradient of this function f dot this di1 vector. Okay, and this di1 vector is the simply the direction in which I am going. Okay, and if you go one step forward, we discussed that df by, let's say this di1 is given by del f dot this whatever the unit vector would be, because when you will divide this di1 vector by di1 magnitude, then you will be getting simply the unit vector in that direction. Okay, so if you remember, we derived this expression, or if you go one step backward, then this is the step we have derived. Okay, now this is the simple change in the height of this function. If you go from point A to point A1, and this change is given by this vector. Okay, this is the vector di1. Okay, now let's say instead of going this infinitesimal small, I want to go from point A to some, let's say, point B. Okay, and now I want to find the total change in the height of that. Let's say this is kind of ceiling. Okay, just assume this is ceiling of any house or whatever. Okay, now we from point A to point B, we want to find the total change in the height of that value f, or you can say that we want to find the change in the value of this function fxy. Okay, so what we can do, let me remove that. So what we can do, let's say from point A, I moved a infinitesimal small distance, which is given by, let's say, di1. Yes, and we found some change in the height of this function, and then from this point, let's say we moved little more further. Yes, this is, let's say, given by di2. Then we will find some change in this height, little bit increment would be there. Yes, so like in this manner, proceeding with these infinitesimal steps, we will make the journey to the point B. Yes, and at this point B, the height would be simply this. Yes. Now the total change I can write. So this is the uh, change in the function when you go infinitesimal small distance. So likewise, if we add up all the change, then we can find the total change from point A to point B as from point A to point B. I can write total change as del f and dot d I, let's say. Okay, this is vector. Okay, so in this way I can find the total change in the function value. Yes, this would be the total change from point A to point B. Now if you look at carefully, okay, this is the one way you can find the change in the value of this function. Now there is second way. Okay, let me remove this also. Okay, so this was our path. Okay, point A to point B. Now, okay, I have removed this also. So this was like that. Okay, now if I want to find the change directly from point A to point B, we can say, okay, height of this function at, let's say, this point A is given by h1. Okay, this height is given by h1, and at this point, let's say this is my height and this is given by h2. Okay, then the total change from point A to point B in the height would be simply we can get f of B minus f of A. Yes, so you can just calculate the height at point B and then subtract the height at A. Yes, so this would be the total change, and this we also have discussed that we can also get this change from going from point A to point B in the infinitesimal steps. So what I want to say that this is what I want to say. Yes, so the total change in the function value is given by this, and which is equal to, fortunately, fb minus fa. Yes, so just remember this expression. This is the fundamental theorem. Fundamental theorem for gradient. Okay, so if you want to find the total change in the function value, and the function is given by this f of x by, then you can find the total change directly from the endpoints. Okay, just calculate the height at point B and then subtract the height at point A. Okay, and the expression of this total change is given by this. Okay, so this is the expression. Let's say this is the equation 1. Now in the last lecture, what I discussed, that the line integral of, let's say, vector b is given by, let's say I am going in from path A to point A to point B. Okay. So let's say this is my some vector field. Okay, and I'm going from point A to point B, then the line integral is given by p dot dl from point A to point B along this path C. Okay, this line integral part we have discussed in the last lecture, so just I'm reviewing that here. Okay, so this was the line integral. Now what I'm saying that if I can represent this vector b as some gradient of some function, let's say this is my capital F. Okay, if I can represent somehow this vector b as gradient of some function f, then I can write this line integral as a to b delta f dot dl vector, and from this equation 1 I can say this would be simply equal to f of b minus f of a. Yes, so in this way we can directly calculate this line integral as f of b minus f of a. Yes, now what is the condition? So let me write it. So I can write a line integral along a path C. Let's say line integral is of vector b. I can write this as f of b minus f of a. That means the line integral is only depending on the endpoints b and a. Now when I can write this, I can write this only if I can represent this vector b is equal to gradient of some function f. Yes, and that is also, if this condition is satisfied, then we call this vector b is conservative. Okay, so if this condition is satisfied, that means if I can write any vector as gradient of any other scalar function. Okay, this f is scalar function. Remember what we have discussed in the lecture of the gradient. So this is simply the scalar function. So if I can write any vector as the gradient of any scalar function, then I can write the line integral in this manner, and that means the line integral does not depend on the path, because you are calculating the line integral just from the endpoints. Okay, so let me again write. So if you are going from point A to point B, so if you also go from point A to point B in this manner, it does not matter. Only the value at the end points is which is mattering for us. Yes. So if you want to find any line integral along this path, you can also say that the line integral along this path C2 is same as the line integral along this path C1. Or directly I would say that line integral depends or does not depend on the path if this condition is satisfied, or I would say if the vector is conservative, then the line integral is path independent. Okay.